Thank you, Stéphane, for this kind introduction. Ladies and gentlemen, it's my pleasure today to talk about non-alcoholic beverage and low-alcoholic beverage produced through fermentation. I want really to thank you for being with us and this very important moment that we want to share with you. So let's see a little bit as an introduction how evolved the market of this non-alcoholic beer. I will not go really in detail, but we see immediately that the growing will go very fast. So it exists for sure different methods to produce non-alcoholic beverage. One of the methods is using a capex. It will not be my talk today for this part of the presentation. We can use as well a stopped fermentation process, which is not my talk of today. I want to focus today on a high temperature mashing with a regular yeast strain for the production of low alcohol beer. And as a definition, the low alcohol beer will be below 2.5 EBV. This is very important to have it in mind. The second subject matter of today is the use of specific microorganisms for the production of non-alcohol beer. And it is below 0.5 EBV. And so in this presentation, I will show and detail a bit the non-Saccharomyces organism compared to Saccharomyces organism. So I start with the low alcohol beer with the lager and the ale yeast strain from the Fermentis collection. So we had a set of experimental, and I will show you here some details of these experimental conditions that were produced in a 50-liter trial of the pilot plant. So we use a composition of 100% Pils malt, and the brewing was at unique temperature, 75 degrees C, during 20 minutes, and the bitterness that we want to follow was 20 BU. It's important to notice that this equipment we use a Mura filter 2001 for the word filtration. The gravity was 10 Plato, and we use different yeast strains from our collection, so the SAF lager S23, S189, as you know, W3470, pitch at 100 grams per hectoliter and fermented at 14 degrees C. For the ale yeast, we have the SAF ale, as you know, T58, S33, and so on. But we ferment at different conditions, at 20 degrees C, and the pitching rate was adapted to 50 grams per hectoliter. The maturation was quite classic at 7 days at 4 degrees C, before we had a dilution to get the alcohol that we want to reach, and the filtration at the beer. So the target was 2.5 ABV, and we anticipate to have an original gravity of the world between 8 and 10 Plato. So let's see a little bit what we did. Here we see that the mashing was at unique temperature, as mentioned. We started 75 degrees C, but the total time that was anticipated at 20 minutes was a little bit above, and in reality was close to 32 minutes. I will see the impact of this time at 75 degrees C. We see immediately here in this cinetic that the limit was a little bit lower than expected, and we get for most of our yeast a limit of about 2 Plato, which corresponds to an apparent degree of fermentation close to 75%, except for 2 yeast strains, the S33 and the S04, where we have an apparent degree of fermentation between 60 and 70%. And we see here in the graph that the limit is between 4 and 3 degree Plato. In terms of sugar analysis, which is quite important, we see that the consumption of the sugar are basically similar for all our yeast strains, except for the S33. And we know in advance that S33 do not consume maltotriose. It is important because it's a maltotriose negative yeast strain. In terms of alcohol production, we see here that we are a little bit above what we expected, and we diluted at 8 Plato to get something that is close to 2.5, at least for S33. But for the other yeast strains, we are a little bit above this 2.5. We decide in these experiments to dilute all the beer at the same gravity to be a little bit more consistent. It could be as well possible to dilute all the beers to 2.5, but here it was a decision that we take. An important effect of this process as well is the diacetyl production. And it is not a surprise to see here that the SAF ale produce less diacetyl and consume, let's say, more diacetyl than a lager, where we are a little bit above the threshold, certainly at 8-degree Plato. So we will see in terms of tasting what will be the results. And if we look to other aromatic compounds here, there is some significant amount of aromatic fraction, which is quite interesting, but for sure we have a higher degree of fermentation than expected. And the higher level of alcohol was obtained and reached with the SAF ale BE256, and the higher ester production was with the SAF ale T58. Here are the results of the tasting, and we can see not much differences between the yeast, but there is one maybe that presents a typicity in these, and it is about the fruity aroma. And we see that S23 is probably the best lager solution that we can offer due to this fruitiness. If we look to the ale beer and we compare them, we see as well big differences here, because there is one that we identify immediately with a different profile, which is the SAF ale T58, which is with a phenolic character and pronounced character. There is one presenting as well a little bit off notes, but it's just one experience, and is the 256, the BE256. But one other interesting yeast strain is the S33, the SAF ale S33, that produce a little bit more fruitiness than the other. So if we have a recommendation, would be in the ale, those two yeast strains. So our recollection due to this process is probably the Mura filter 2001, which is using a fine coarse milling, seems to increase the enzymatic activities during the brewing step, which means that we have a higher degradation than expected. If we look to the objective of the production of the 2.5 EBV with a gravity between 8 and 10 Plato, we can recommend using a composition of 100% of malt pills with a brewing that we can adapt. And let's say that we have to monitor initially what is the gelatinization point of the malt that are including in the composition, and it's probably close to 75 degrees C. And if we use a 2001 mesh filter and not the 2201, I'm sorry for that, we have to reduce the contact time to about 10 minutes as a maximum to expect having a lower degree of fermentation. And if there is a low to ton, the contact time could be between 15 and 20 minutes. For the yeast strain, our recollection would be for the ale to have a SAF ale S33, which is the non-phenolic and probably producing a little bit more fruitiness. And if you look for a phenolic solution, which is nice, we have the SAF ale T58. For the lager production, we recommend the SAF lager S23 with slightly more fruitiness as well in these compositions.
So, Philippe, so you reckon that high temperature mashing is a feasible or interesting solution for brewers of a certain size primarily, probably. It's an interesting solution to produce low alcohol beers, but there are some points of attention.
Absolutely, this is completely clear. And for sure, it needs to be adapted according to the raw materials that are using, and certainly the process. And the process, I really need to focus on it. It's your process. You know your process. It's for sure depending on the milling conditions, where you put the malt and the water, what temperature, what time contact, and what equipment of the filtration, and how it occurs. So it's really critical. And it's really a little bit your responsibility, brewer, and I really talk to you to adapt it. And you may make some trials initially and adapt it, because it's completely difficult to get it at the first time. So it's my recommendation.
And milling, mashing, filtration is really key. It's quite essential.
Absolutely. Temperature and time to be controlled. Yes.
Thank you.
Yeah, you're welcome. So the second part of this talk will be dedicated to the non-alcoholic beer with specific and non-specific microorganisms. So here, I will talk about some maltose negative microorganism, because if we want to have some low alcoholic beer beverage and non-alcoholic beer beverage, we need to use a maltose negative yeast strains.
So I just want to stop you here for a second, Philippe. So yes, the previous part was clearly targeting less than 2.5% alcohol. Here you're getting in what? What's the target?
It doesn't work. It's below 0.5. So it's the target is below 0.5. I'm sorry, and thank you for these comments. It's very critical that we are precise and everyone understand that we are below 0.5 EBV.
So the high temperature mashing aims at less than 2.5, can be lower, but not in all conditions. And then here in this case with some other microorganisms, you can reach less than 0.5.
So there will be, here you will see a normal, let's say, process, but the specificity is the microorganism. On the first part, as you mentioned, there was a process that was specific with a regular yeast strain. So here, the objective is to use maltose negative yeast strains. And so we use several microorganisms. It was the Saccharomyces chevalieri, that was from the Le Saffre collection. And we look to external collection, the NCORC, where we identify a Pichia cloyveri, a Saccharomyces ludwigi, a Toilaspora delbrueckii, and a Zygosaccharomyces ruxi. So it was, the experimental protocol was a classical word, as mentioned before, the no specificity, so a malt composition 100%. The diagram was classic with 65 degrees C for 50 minutes, 73 for 10 minutes, and we produce at a 12 Plato with a mosaic hops for a target of 25 BU. Temperature of fermentation was here two conditions for the Saccharomyces chevalieri, only one condition, 22 degrees C, for all the microorganism. And we dilute, the target was a dilution at 8 Plato to get something close to 16 BU, corresponding to about 0.5 EBV. We'll see the results here. But a big difference between, let's say, a regular Saccharomyces cerevisiae and other is in the way they assimilate the sugar. So here I briefly put a standard composition and a typical word coming from the brewing industry, and we see in terms of weight, percentage, that the glucose corresponds to about 10–15%. The maltose is the large part of the sugar, between 50 and 60. The maltotriose could be between 10 and 20%, and the dextrin, which is the higher level of the sugar, between 15 and 20% in weight. So, looking to the assimilation of the sugar, on the left side you have the wort, which is the standard. On the right side we have the chevalieri, and we see that the chevalieri do not consume the maltose, because the level is the same as the wort. And we see that the other microorganisms that were identified as maltose negative probably assimilate very slowly the maltotriose. And in terms of ethanol production, we see as well that we are completely standard, because the chevalieri produce about 1 EBV, and there are some microorganisms consuming a little bit more, with the higher level of alcohol a little bit above 1, but it's not really critical at that step. But what is important to notice that maybe some other microorganisms than the Chevalieri may consume fraction of maltose. So, for sure, if those microorganisms consume slightly part of the maltose, it may affect the attenuation with the alcohol production, as we have seen, but as well the carbonation of the beer after. We are certain that with the Chevalieri, all the maltose are not consumed and the fermentation stops automatically with no risk of higher attenuation and over-saturation. In terms of tasting,
Philippe,
yes?
Can I interrupt you just for a second here, because I think there is something important to mention. In any case, because you could always have in the process somehow, even with the raw materials, you could always have introduction of a maltose positive microorganism in the process. So in any case, I think we recommend to pasteurize the beer, sure, whether you use a Chevalieri or another one. Sure. So in both cases, whatever happens, even if you have a maltose positive slow, yes, you will actually inhibit or yes, inactivate this yeast in any case.
This is absolutely correct. I will come a little bit later on the pasteurization that is absolutely mandatory in this type of process to avoid complete oversaturation and explosion of bottles, because if there is a contamination somewhere, for sure the fermentation will continue in the bottle with all the risks that it affects and contain. Absolutely, this is totally correct, and thank you for mentioning it. It's really important to notice it. So to come back to the tasting results, we have seen that the Torula Spora produce more a neutral, malty, wort-y beer. The Ludwigi was a little bit more artificial with some notes of DMS and some taster detect some plastic, but as well a balance with the fruitiness was identified. The Ruxi produced a lot of flavor. We don't really recommend. The Piccia was really, really fruity with a lot of production of isoamyl acetate, which is the banana flavor. And the Saccharomyces Chevalieri produced a very well balanced beer with a slightly note of phenol character because it's a POF positive yeast strains. So today, from all those microorganisms, we have selected the SafBrew LA-01, which is the Chevalieri, for the rest of our protocol. So here in this experiment, we will use the SafBrew LA-01 at 50 gram hectoliters in a Weyermann wort of 15 Plato, and we will ferment it at 20 degrees C, or is realized in flask. So we see that at different gravity, so we had 6 Plato till 15 Plato, that does not affect really the limit in terms of time. So it means that the limit is reached after 60 hours. And it's really important to know that the process is quite fast and we don't need to wait for weeks, because if we wait for weeks, the risk of over-carbonation, over-saturation, over-fermentation may occur if there is a contamination somewhere. So, in terms of apparent degree of fermentation, we see that everything is ranging between 13 and 14. If we remember the composition, the typical composition of a wort, the glucose were between 10 and 15% in weight, and we are completely within these limits. Even if the scale is starting at 12, the difference is really marginal. The sugar composition as well, because we see here the wort, and if we focus on the simple sugar, which are the fructose and the glucose, we see that are consumed completely, but the DP2, which is the maltose, is not consumed, and the DP3 for sure neither, which is the maltotriose. In terms of ethanol, for sure it follow a little bit the same rules as the gravity, because the more gravity, the more alcohol, which is logical. And we try to correlate the gravity and the ethanol production, and we obtain a very nice linear regression where we can anticipate the level of alcohol or the gravity we need to get the 0.5 EBV. And here, in this example, we can say that 0.5 EBV can be reached with a gravity ranging between 7 and 8 Plato. The volatile compounds are quite significant because we see at least something. We had some acetaldehyde produced, which is not necessarily negative in these type of beers. The isoamyl alcohol is for sure a little bit before the threshold, and as well as the isobutanol and the diacetyl, hopefully. But all those compounds may act with a synergetical effect that produce a certain balance of the product. We see as well at a different temperature, at least for the SafBrew LA-01, at 10 degrees C, that we have more, let's say, ethanol production, and we go faster and higher in fermentation with a higher temperature. So the SafBrew LA-01 should be fermented at higher temperature than 10 degrees C. As a first conclusion, we can say that the SafBrew LA-01 produces a well-balanced beer with slightly phenolic, but preferably fermented above 10 degrees C. It contains some residual sugar, and therefore the beer is fragile, and in that respect, we need to consider an additional process as the pasteurization. And we will see a little bit more in detail what we perform here. So we had a wort fermented with the SafBrew LA-01 at 25 degrees C. We centrifuge, and we intentionally cross-contaminate with a yeast, a T58, at different level of contamination, 0 CFU per ml till 10 to the 5 CFU per ml. So we have a significant amount of contamination in this beer. We pasteurize at 63 degrees C, and we calculate for sure the pasteurization time according to the formula that you probably know. We sequence with no latency, so immediately after the contamination, we pasteurize at different level, 25, 50, 75, 100 PU, and then we plate with a media to allow all the microorganisms to grow. We see in this graph that 25 PU, significant amounts of yeast continue to grow and are identified, so it's not enough. Because we can consider generally 25 PU for a pills process as a guarantee and enough, but in this product it's not enough. And at 50 PU, it completely disappeared. There is no presence of the T58 in this case. So as a recommendation, we can say that a minimum of 50 PU is recommended and mandatory. If we go now to the main conclusion of this talk, we can say that the pitching rate is exactly the same as we can have with the SAF ale, so it's 50 grams per hectoliters. The fermentation temperature that we recommend are between 15 and 25 degrees C, with an apparent degree of fermentation of about 15%, with using a traditional brewing diagram. The alcohol of about 0.5 EBV will be reached with an original gravity ranging between 7 and 8 Plato. And the pH will be close to 4.5 with that. So it guarantees as well some protection due to the low pH. There is no off flavor. This is a good point. The pasteurization should be between 50 as a minimum till 100 PU. It is a product that could not be reused for repitching, and certainly not for refermentation. I can't finish this talk before thanking our partner, which are Meurice Institute and KU Leuven, as well as the technical team of Fermentis. So thank you very much for your kind attention.